Okay, same logic is in the simple slab. Little w is supposed to have pounds per foot. I have pounds per square foot. We have a 1 foot wide strip. Therefore, this can be done fairly easy. Only reason it can be changed is we've got a 1 foot wide strip. Okay, so there's my load. Now, here's a diversion, letter D. Okay, now, last time we took W. We ended up with an equation that looks like this last time. M equals WL squared, little w, L squared over 8. I told you the 1/8 was the moment factor. Okay? In this, we don't have 1/8. You don't see an 8 anywhere. Minus a 12 plus minus. Okay, we're checking concrete here. So letter D, if you read it. The moment generated by the loads will vary throughout the slab's length. Therefore, we will use the largest moment to check the required effective depth of the concrete. Okay, so if I look at those, if I put an equation that looks like this, mu is equal to u times L squared over 8 or multiplied by C. So I'm going to do this. I'm going to take this, instead of putting that 8 down there like I did before, I'm going to do this. C, moment coefficient, times UL squared. So U is what, 251? So let's do this. Okay? Now the C we used to use is positive 1/8. Now I got a choice. I could pick any of these guys. Minus 1/12, 1/14, and so on. Since it varies and the concrete moment varies, we want the worst case. So what number gives me the biggest moment? If I multiply it by 1/12, by 1/14, by 1/10, by 1/16. Well, hopefully you see that if I multiply it by 1/10, I get the worst case or the biggest moment. So here, we're going to do it by so there's the worst moment in that particular slab. So I'm going to take 251, which is little WU. 251, I'm going to multiply it by 11 squared, and I'm going to divide that by 10. 3037.1. 3037.1. Foot-pounds. Why is it foot-pounds? 251 is pounds per foot. That is feet squared. Feet squared times pounds per foot gives me foot-pounds of moment. Okay, so there's the moment, and I'm going to do something right here quick. 3037.1 foot-pounds of moment is equivalent to how many inch kips of moment? 3037 times 12, changes to inches, divided by 1,000. 36.45. 36.45 inch kips. I need that number. Okay? That number's a good one. I got to have that. So a couple numbers up here I don't want to lose track of. That's one of them. That's one of them. And that's one of them. Well, that pen doesn't work too well. Let me redo this. So these three numbers, actually four numbers, are pretty important to me. Okay? So now we've got the moment. So we've just finished letter D. Let's go to letter E, apply the resistance factor to it. So I'm going to take that, the E, R equals 3645 divided by 0.9 divided by 0.9 gives me 4050. So I end up with 4050, and actually that is the real important number for me. So I'm going to give him a little special treatment there. So I need him. There's the moment generated in the worst case in the beam spans. So I've got that. So let's move on. Determine D of the section thickness. Determine D of the section thickness determined in step A. D is equal to the thickness minus half the bar diameter minus the cover. Once again, just like we did in the unit associated with simple slabs, I'm going to give you the size of the bar, so you're not going to have to guess it. I'm going to kind of use what they've done in the past here. So I'm going to do letter F. Letter A, I picked 5.5. So D equals T minus cover minus half of bar diameter, and I'm going to pick a number 4. So D for the section I picked is 4.5 inches. Okay? So we're in pretty good shape there. Now we're going to use the balance section data to figure out how much this slab can resist. So letter G. And if I do this the way you've done it in the past, I'm going to use this as MR star, just like I've done. So what am I going to do now? This is what it's got to carry. This is what it can carry. So where do you get the R? Same place you've always got it. Go back to page 423. What's my material specs? There's 423. I have got concrete of 60, or of steel of 60, concrete of 4. 60 and 4 gives me a number of 1.417 for R. 1.417. B is always 12 inches because that's the width of our strip. I just figured D to be 4.5 inches. I'll square that. I'll multiply it out. That's going to tell me exactly how much moment that section can resist. So 117 times 12 times 4.5 squared. 344.3. Okay, this is what I need. This is what that particular cross-section can provide. I need 40.5 inch kips of resistance. I have 344 inch kips of resistance. What does that tell me? Tell me it's got a section that has plenty of depth to take care of flexure. So flexure's out of our life now. So we've checked it and made sure the bending was okay. So take the MR calculated here and change the units, okay? You got your choice, doesn't matter to me. You can leave this in foot pounds and change this to foot pounds. I change this to inch kips, and then I can compare it directly. Just make sure your units are all compatible. That gets us through letter H. Flip the page. Compare this value to the one calculated in step E. We're fine. this number compared to this number. 9 times. We got plenty. So now we're going to check shear. So we're on letter J. So I'm going to go ahead and check shear, and I think I can get rid of some of this stuff. I need that over there to finish off the, I'm going to get rid of that part. And I'm going to write this here. And I'm going to leave 11 feet here. And I think I don't need this anymore then. Okay, let's move on to letter I. We did letter J. So I'm in shear here. Letter J. The shear in it. Now I'm going to combine these two, okay? Let's do VU. Safety factor, load, span. I don't know if you can see that, but I just did. Hopefully you can. That finds the reaction on the left-hand side multiplied by a safety factor. So 251 times 11 times 1.15 divided by 2. 1,587 pounds. Then move down to the next step. Same letter, one more step. Divide this by 0.75. Once again, that's the resistance factor. Divided by 0.75. 2117. So there's the shear that exists at the worst possible place in that particular section. Compare it to K. It says VC is equal to 2 type of concrete, which is 4,000, times B, which is always 12, times D, which was 4.5. Okay, this is the ability. This is need, have. So let's take the square root of 4,000. We're going to take that and we're going to multiply it by 2. We'll multiply it by 12 and we're going to multiply it by 4.5, 6831. Okay, what have we done here? We've checked what we need versus what we have. We have more than we need. Shear is okay. So what have we got now? We've got ourselves a 3-pronger. We've checked a thickness for deflection. Found out it was 5.5 inches. We made sure it was good in bending, which we proved it was good by about a factor of 9. And then we checked the shear, and by a factor of about 3, it is good. So the 5.5 inches is governed by deflection, and it's going to rule because all the rest pale in reference to that. So I've basically have cemented myself into a thickness of 5.5 inches now. Okay, it says letter L. You have now chosen the depth based on one of 3 criteria. If the depth was not chosen based on flexure, we must revise the AD ratio and reduce the amount of steel, basically. Determine the final effective depth of the slab. We already did that. There's the final effective depth. Okay, determine AD for the balance section. So I'm going to go to the table. And I'm going to look up concrete and steel of 4,060 and get myself a value for AD. Page 423. 60 and 4, 0.592. AD table. Table, page 423. So that's letter N. Revise AD to reflect the under-reinforced. Use AD revised equal to 0.4. Okay, that's the number you're going to use. Okay, so letter O. AD revised is equal to 0.40. Okay, now it says go through a check. If you'd like to, I will allow you to do this fairly easily. Just put an X through letter P. We're not going to do that. I'm not going to have you go through that check. It is something we would do as an engineer, but you as a design professional that's limited to construction only, don't worry about it. So letter P is kind of mute. Okay, we're done with all of our checks. We've got AD revised whipped right there. So what are we going to do next? AD revised from step O and M. Okay. Revise AD to reflect the under-reinforced condition. Use AD revise equal to 0.4. This value can be verified, so P we're not going to do. So we move on to Q. Since the moment factor varies several times throughout the slab, minus 1/12, 14th, 10th, 16th, 12th, that's what we're talking about there. Since it varies, we're going to use the letter C as a generic number in our formula, and then later apply the C to each of those locations. So now what do we got to do? We're going to find a moment in generic form. So that's letter Q. So let me do this. We've got this pretty well taken care of. So generic form, letter Q. Hopefully this doesn't screw you up. I would write that C right away and put him over here. Okay? Then I would fill in the blanks. U, 251. L squared, 11 squared. Look familiar? Should. Okay, 0.9 phi. So there's our equation. Now I got to make sure my units. I'm in pounds and feet. Okay? Depends on how you want to do it. You could do that. M's typically are in inch kips. So if I want to make that into inch kips, if I'm in pounds